Welcome to the video lecture on polynomials. A polynomial function is a function constructed using the operations of addition, subtraction, and multiplication. We say that a polynomial function p of degree n is a function of the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 and so on down to a sub 2x squared plus a sub 1x plus a sub 0. So it's basically made up of things called coefficients. All of these a sub i's are called the coefficients, multiplied by powers of x's, and then these terms are either added or subtracted together. The a sub n coefficient has to not be 0 if this is considered a degree n polynomial, and we need all the powers on the x's to be positive integers. So they need to be numbers like 0, 1, 2, 3, 4, 5, and so on. Some examples of things that would not be polynomials would be things that have x's raised to non-positive integers. So you might see something like a square root of x, which is really x raised to a 1/2 power. So any x's raised to fractions or decimal powers would not be considered polynomials. Or if you saw 1 over x, that's really a negative exponent, like x to the negative 1 or x to the negative 2. So if you saw any expressions with x's raised to negative powers, then that also is not considered a polynomial. So again, the a sub i's are called the coefficients. They can be any real number at all. The a sub n is called the leading coefficient, and the a sub 0 on the end is called the constant coefficient. If you only have one single term in your polynomial, then it's called a monomial. Now, polynomials are extremely important in mathematics and science because almost every function in math and science uses polynomials or can be evaluated by using polynomials. For example, a lot of the things that we ask our calculator to approximate for us, like sine of pi over 2, cosine of pi over 6, various values like that, your calculator is actually using a polynomial approximation to figure out these exponential, trigonometric, and logarithmic type of functions. For example, e to the x, it turns out, is the infinite polynomial 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. And this does go on forever. So this is an infinite polynomial. Likewise, sine of x can also be proven to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. So these infinite polynomials are a way for a calculator to evaluate trigonometric and exponential functions. And all of these things would be proven in calculus if you go that high in mathematics. So if your calculator wanted to figure out e to the first power, then it would plug in 1 for all of these x's and then figure out what that approximation turns out to be. So polynomials are very important in math and science. What we're going to talk about in this lecture is predominantly some general characteristics that all polynomials have, especially graphical characteristics. So the first thing that we're going to show is that all polynomials are considered smooth and continuous. This means that they have no breaks, no holes, corners, or cusps in their graphs. And continuous means that you can put your pencil down and draw the entire graph without ever once lifting your pencil. So for example, if I put my pencil down and I just keep drawing like this, that's a nice, smooth, continuous polynomial graph right there. What you wouldn't want to see, something that's not smooth or continuous, would be something that has maybe a jump in the graph. So I go here and then I jump up and then I start drawing the graph again. Or maybe something with a hole in it, or something with a sharp point or cusp in it, or maybe something with an asymptote, vertical asymptote or horizontal asymptote, something like that. Okay? So this would not be a nice, smooth, continuous function. So what we're going to look at are just some very basic power functions, x raised to various powers, and we're going to try to determine what some of the characteristics of these graphs are. And when we graph these, I'm going to graph several odd ones on the same graph and then several even ones on the same graph. So let's go to our calculator and let's go to y equals, and let's do the odd ones first. So I'm going to type in x in y1, and then I'm going to type in x cubed, or x to the third, in y2, and then in y3 I'll do x to the fifth. Whoops, I have an extra number here. And then let's do x to the seventh. And let's start with a window that goes from -5 to 5 for x's and -5 to 5 for the y's. We'll start with that and hit graph. There's y equals x. Here's x cubed. Here's x to the fifth. And there's x to the seventh. And they start to get pretty close together, so it's hard to see them up close. So let's narrow our window slightly and change this to -2 to 2 for the x's and -3 to 3 for the y's. And hit graph. So there's y equals x. Here's x cubed. Here's x to the fifth. And here's x to the seventh. So some of the characteristics that you want to see, look at the change in the graph. It starts low and it ends high. So we call that the end behavior or tail behavior. And what we're going to show in just a few minutes is that as you go to the left towards these -infinity x values, the graph goes down, so y goes to -infinity as well. And if I go to the right, or as x goes to +infinity, the graph goes up, so the y values go to +infinity as well. So this graph increases. I also want you to note here that the higher this power gets, the flatter in the middle near the origin here that it gets as well, and the steeper that it gets going up and down. So we'll see that trend continue as well when we take a look at the even powers. So let's go ahead and go back to y equals, and let's change these to x squared, x to the fourth, x to the sixth, and x to the eighth. And we'll leave the window the way it is for now and hit graph. So here's x squared, here's x to the fourth, x to the sixth, and x to the eighth. So now let's take a look at the end behavior of these graphs. They go up on the left and up on the right. So as x goes to minus or plus infinity, the y values go up to +infinity as well. So they go up, up on both sides. Also, as the power increases, the graph gets flatter down here at the bottom near the origin, and then rises up much steeper going up towards that infinity. So let's go ahead and take those characteristics and make sort of a little table that generalizes what we know about this power function x to the n. And it depends on the degree. So let's start by talking about our even degree polynomials, since we have that picture showing right now. And let's first talk about the tail behavior. So again, this is assuming that this power n is something even, like an x squared, x to the fourth, x to the sixth, and so on. Assuming that this is an even power, and I'm also going to assume that the leading coefficient here is positive. So it's a positive x squared, a positive x to the fourth, positive x to the sixth, and so on. Then you have the following end or tail behavior. It would look like this: up, up on the left and the right. And this is assuming that a sub n is greater than 0 or positive. And the a sub n here is that leading coefficient. And if we just have an x to the n, then that coefficient would be a 1. But I also want to take a look at what would happen if that leading coefficient were negative. And we'll do that in a moment. Now, this is my end or tail behavior. It goes up, up on both sides. I'm going to show you an alternative way to write that. What we could say is that y, the y values, go to positive infinity as x goes to positive infinity. That would be this direction over here. As x goes this way, the y's go up. That's what I mean by this statement right here. If we take a look at the other direction, so if I go this way, as x goes to minus infinity, what do the y values do? They also go up. So y continues to go to positive infinity as well. So that's just an alternative way that you could write that tail behavior using these arrows and the infinities. Now, what would the tail behavior be if this leading coefficient was negative? Well, if your leading coefficient is negative, that would be like multiplying this by a minus sign. And remember, if you multiply the outside of your function by a minus, that's a reflection over the x-axis. So all that's going to do to our graph is flip it upside down. So then our tail behavior would go down, down. And if we wanted to write that using this new notation, as I go to positive infinity, so as I go this way on my graph, the y values have to shoot down. So we would say that y goes to minus infinity as x goes to positive infinity. And if we go in the other direction this way, as x goes to minus infinity, also the y's have to shoot down as well, so y continues to go to minus infinity also. So those are our two tail behaviors depending on whether that leading coefficient is positive or negative. If you take a look at these graphs that we had over here, what kind of symmetry do they have? They are reflections across that y-axis. So this would be y-axis symmetry, and that's another name for being an even function, which makes sense since we have an even power. Let's talk about the domain as well. What's the domain of these graphs? What could x equal? Well, for any polynomial, no matter what power it is or what degree it is, the domain is always all real numbers, minus infinity to infinity. You can let x be anything at all, and you'll never have to worry about, say, dividing by 0 or taking the square root of a negative. You won't have those issues with a polynomial function. What about the range? Well, the range does depend on the actual polynomial, but if we are just looking at a simple power function, x raised to a power, then it's going to hit that origin but stay above it if your leading coefficient is positive here. So this would be 0 to infinity if the graph is going up, up, and it would be minus infinity up to 0 if the graph had started below that x-axis, if that leading coefficient had been negative. Okay? One other comment I want to make here before we move on again is that the bigger the power, so the larger that exponent gets, the flatter the graph gets near 0, near the origin, and the steeper it gets. And we saw that over here where the graph started to look almost very flat like this when we did x to the 8th. So it's very flat across the bottom and it rises up very quickly on the sides. So that's what I mean about it being flat near the origin but getting steeper. Okay, so now let's take a look at our odd degree polynomials. And if we need to, we can go back and change some of these so we can refer to our pictures. Oops. So x, I'll do x cubed, I'll do x to the 5th, and I'll do x to the 7th, so those odd powers. And we're going to talk about end behavior here first. And again, let's assume initially that this a sub n is greater than 0, so that leading coefficient is positive, which is what all of these were because we had x, x cubed, x to the 5th, x to the 7th. What kind of end or tail behavior do they have? Well, they start low, shooting down on the left, and they go high, shooting up on the right. Let's write that using our arrows and our infinities. So if x is going to positive infinity. So if the graph is going this way, on this side of the graph towards those positive x values, what are the y values doing? They're going up. So we would say that y goes to positive infinity as x goes to positive infinity. Now let's look in the other direction. So now we're going to go towards the negative x's. So if I go this way and look this way on my graph, as x goes to minus infinity, what do the y values do? They shoot down. So we would say that y's go towards minus infinity. So that's how we write our tail behavior for that positive leading coefficient. So what would we say then if the leading coefficient was negative? Well, again, that's just a reflection over the x-axis. So if we put negatives in front of all these equations, this would just reflect upside down. So all these bottom pieces of the graph would go up, and all these pieces that go up on the right would now shoot down. So we're just going to get the same end behavior that we had up here, but flipped over. So we'd go up on the left and down on the right. So now the graph would decrease instead of increase. So let's fill in our little chart. As x goes to positive infinity this way, this direction, what are these y values doing? They're going down now. So y is going to minus infinity. And if we look in the other direction, if I go this way on my graph, as x goes to minus infinity, these y's now are going to be shooting up instead. So y would be going to plus infinity. Okay, so there's our tail behavior. Look at our graph over here. What kind of symmetry does this graph have? It's not even because we don't have a reflection over that y-axis. It's not symmetric over the x-axis because we don't have that type of symmetry, but it does have symmetry about the origin. If you were to rotate this graph 180 degrees, you'd get that mirror image. So this has origin symmetry. And we know another name for that. We also would say that that means that this is an odd function, which again makes sense because we were talking about odd powers. Okay, how about the domain? Well, just as I said before, with the even powers, this is true of all polynomials. The domain of every polynomial is always all reals, no matter what power you have or what terms you have. So every x is allowed. If the graph has a positive leading coefficient with this kind of tail behavior, what would its range be? And you can see that from these graphs over here. What's the range of all of these odd powered graphs? Well, they shoot all the way down and they shoot all the way up. So here the range would be minus infinity to infinity. And if I were to flip that over the x-axis, the range wouldn't change at all. I would still be going all the way up and then all the way down. So my range is going to be all reals as well whenever I have an odd degree polynomial. And then one last comment here, again, very similar to what we said up here about the even powers. The bigger the power, the flatter the graph is going to get near the origin and the steeper it will get on the sides. So the higher the power, the flatter the graph gets near the origin. So as these powers get bigger, this is going to look more like this as opposed to this. Okay, that's what I mean by flatter right in here. And the steeper it gets on the sides. So it's going to rise up to those infinities or minus infinities faster than it would if it had a smaller power. Okay? Now, all of these conclusions that we just talked about were for the very basic power function x to the n, and that doesn't involve or include any consideration of shifting these graphs, flipping them over, moving them up or moving them down, doing any of those kinds of transformations. So that's what we're going to talk about next, and we're going to talk about how to sketch the graphs of these things keeping in consideration our characteristics, but also using some of those common transformations that we've done in the past. So let's take a look at this first function. It's minus parentheses x minus 3 raised to the 5th power. So we know that this is an odd degree up here, a 5th power. So what we want to be able to tell right off the bat here is, since it's degree 5, that means we know that its tail behavior is going to be either down up or up down, and which one it is depends on the leading coefficient, whether it's positive or negative. And the fact that we have this negative out front is going to tell us that we'd have, if we were to FOIL all this out, which you certainly do not want to do, this would have a leading term of negative x to the 5th power. So it's like a negative x to the 5th, which means, based on our conclusions up here, it has to start high and end low because it was a negative leading coefficient of an odd degree. So the negative x to the 5th tells me that the tail behavior should be up on the left and down on the right. And if you wanted to be fancy about it, you could say that the y's go to positive infinity on the left as x goes to minus infinity, and the y's go to minus infinity on the right as x goes to positive infinity. So that's what these arrows represent. What else do we know about this graph? Because it was degree 5, we also know that it's going to be fairly steep, and it's also going to be a little flat as well. But this time it's not going to be flat around the origin, because we do have this minus 3 inside of our parentheses. So instead of going through the origin, we are now going to have a horizontal shift going on, because that's what a minus 3 inside the parentheses next to the x tells us to do. So the minus 3 is a shift horizontally which way? Well, remember, horizontal shifts are backwards from what you would expect. So a minus 3, we think left, but it's actually going to go right 3 units. So instead of having this graph be a little bit flat around the origin, now it's going to be flat around x equals to 3. So this is going to be centered right around x equals to 3 because of that shift. So it's your basic x to the 5th graph, but shifted right 3 units. So let's go ahead and put some of these pieces together. We know that it's a little bit flat around that intercept right there. Whoops. And we know that its tail behavior is up and then down. If you want to plot a couple of more points, you certainly could. Sometimes one of the things that I will look for is what the y-intercept is. And remember, the y-intercept is going to be when x is 0. So if I were to plug in 0 for x, this would give me negative 3 raised to the 5th power. Negative 3 to the 5th power is negative 243, but when I multiply it by this negative over here, it becomes positive 243. And that's huge. So that's obviously way off of my graph over here, which is part of the reason why this is going to rise up so steeply. Whoops. So we have that end behavior where it goes up on the left, and then this is flat, and then it goes down on the right. So it would have some similar shape like this, and I'm going to try to round out my edges a little bit. But there's my sketch of my graph. And notice I only plotted one point. I only plotted that x-intercept at 3 due to that shift right. So you don't really need to plot a lot of points here. All I'm really looking for is the general shape of the graph, in that you have the right tail behavior, and you have the right steepness, and you have the areas that are supposed to be flat. So you don't need to be totally accurate in terms of plotting every single dot in the right place. I'm not expecting you to plot points. I'm just expecting you to use these general characteristics that we talked about up here to get a very rough sketch of the curve. So let's try another example. We have negative x to the 6th minus 2. So we know that the leading term here, the dominating term, is this one right here. So we have a negative x to the 6th in front, which means this is an even degreed polynomial, but because the leading coefficient here is a -1, its tail behavior would look like what? Well, remember, even powers either go up, up, or down, down, and if the leading coefficient is negative, then that means it goes down, down. And if you wanted to be fancy about it, you could say that y goes to -infinity as x goes to -infinity, and y goes to -infinity as x goes to +infinity. So it's going down for the y's when I go to the left or to the right. Okay? So we know what our tail behavior should look like. What about where it's going to be centered at? What kind of shifts do we have going on? What does this -2 do to my graph? Well, it's on the outside of the power, so that's important to know. If it's on the outside of the power, away from that x, then that's a vertical shift, and because it's minus, this is going to be a shift down 2 units. So instead of being centered at the origin and looking like a negative x to the 6th, it's going to be centered at a y-intercept of -2. So we're taking that whole x to the 6th graph and just moving it down. Because that power on that 6 is fairly big, this is going to be steep on the sides and also flat as well. So we're going to have kind of this flat part right here, and then it steeply shoots down to the left and down to the right because of that tail behavior. And you want to try to make this as rounded as you can. And there would be our rough sketch of our graph. Alright, let's try some more. Now another thing to consider, we have already done these for our 2 examples here, is we've considered some x-intercepts. So we're going to look at that some more. We would say that a polynomial p of x has a number c such that p of c equals to 0. If p of c equals to 0, then we would say that c is a 0 of the polynomial. So if there's a number that you were to substitute in and it would give you 0 for the y, then that makes c a 0 of the polynomial. Now some other names for this would be that it could be called a solution to the polynomial, or it could be called a root of the polynomial equation, or it would be also an x-intercept on the graph of the polynomial. So what you want to keep in mind is that this word 0 is synonymous with the word solution and with the word root and with the phrase x-intercept. They all mean exactly the same thing. They mean that there's an x value that you plug in, it makes the polynomial 0, which is going to be a 0 or an intercept on your graph. So let's take a look at this function here and let's find its zeros. So technically what you're doing when you're finding a 0 is you're setting your polynomial equal to 0 and you're solving. And on this one we get a little bit lucky because it does factor. We could have an x and an x, a 4 and a 1. If I make the 4 minus and the 1 plus, then I'll get that -3 in the middle. So that means I get x equals to 4 and x equals to -1 as my 2 solutions. So the x-intercepts would be at 4 and -1. So 4 and -1 are called the zeros of the polynomial, they're called the solutions of the polynomial, the roots of the polynomial equation, or the x-intercepts on the graph. So we're going to plot these as x-intercepts. So I'm going to put a dot at 4 and a dot at -1. Now while we're talking about intercepts, let's also find the y-intercept. So that's always a good point to know in your graph, and that should be fairly easy to find because you're just substituting in 0 for x's this time. So this x squared would go to 0, this 3x would go to 0, so all we'd have left would be -4. And that's on the y-axis. So I'm going to put a dot on my y-axis as well. Now once you've found your intercepts and you have your polynomial function, it's always a good idea to consider that tail behavior as well. This has a leading coefficient a leading term of x squared, which is a positive coefficient, and since that's an even power with a positive coefficient, the tail behavior would be up, up on both sides. So what we want to do is sort of put all of these pieces together. We know that we need to go through these 3 dots at the very least, and we need to be up on the left and up on the right. And these are the only 2 x-intercepts of this entire function, so you can't possibly go through and cross that x-axis anywhere else on the graph, only at these 2 dots. So that means to the left of this dot, if I'm supposed to be going up, I'm going to have to stay up. Likewise, to the right of this x-intercept, since I'm not allowed to come back down and hit that x-axis, I'm going to have to stay up and to the right. And there's the correct tail behavior that I'm supposed to have. And now all I need to do is connect this down with that y-intercept and make that parabolic shape, since we know that this is an x squared. So there again is just a very rough sketch of what your graph would look like. And really all I'm expecting you to consider to get your graph are your x-intercepts, your y-intercepts, and that tail behavior. Let's try another one. So here is another quadratic equation. Let's find the x-intercepts first. And in order to do that, we're going to set this equal to 0. And this one, again, does factor. If we do 3x and x, I'm going to have to put the 2 here and the 1 here. That way I'll get a 2x and a 3x in the middle. Let me make the 3x negative and the 2x positive so that I get a minus 1x in the middle. And that means I'm going to get x equals negative 2/3 and x equals 1. So my x-intercepts are negative 2/3 and positive 1. So I'm going to put a dot at approximately where negative 2/3 would be and positive 1. Let's find our y-intercept. So we're going to plug in 0 for x's, which makes both of these terms go to 0, and that would just leave me with the constant negative 2. So I need to hit the y-axis at negative 2. And then if we look at our tail behavior, we are an x squared. The leading coefficient is a positive 3, so that means we have to go up on the left and up on the right. So since these are my only 2 intercepts that I'm allowed to have on that x-axis, and I want to go up on the left and up on the right, it would have to look something like that. And then we'd have to come down, hit that y-intercept, but turn back around to hit our x-intercept. Okay, so the last 2 examples that we did were quadratic equations, and they each had linear factors. That when we factored these, we each had 2 factors with x to the first power. But occasionally when you have a polynomial, it might have factors with higher powers. So for example, p of x equals x minus 3 quantity squared and x plus 5 quantity 3 raised to the 3rd power. And when that happens, we say that those zeros or those solutions have a multiplicity. So this factor x minus 3 would have a solution of 3, and what we say is that 3 is a 0 of multiplicity 2, and negative 5, which is the 0 for this factor, is a 0 of multiplicity 3. And very similar to our statements earlier about getting flatter if the power is higher, the same thing is going to be true here with multiplicity. The higher the multiplicity, the flatter the graph will go through that intercept. And we'll see examples of this in just a moment. So just to summarize what we mentioned earlier, these 4 statements are all equivalent. So we could say that the number c is a 0 of our polynomial p of x. That's the same thing as saying that c is a root or a solution of the polynomial equation p of x equals 0. That's the same thing as saying that x minus c has to be a factor of the polynomial. And it's the same thing as saying that c comma 0 would be an x-intercept on the graph of the polynomial. Okay, so those 4 statements all mean the same thing. It's just a different way of saying the same thing. Now some other characteristics of polynomials. If you have 2 zeros on the graph of a polynomial, between those 2 zeros, the graph has to lie completely above or completely below the x-axis. So you can't cross again in between those two zeros because you've already found all the zeros of your polynomial. You could also take a look at just this very generic polynomial, degree n, with all these other terms, and some of the characteristics that we're going to see happening is that this graph is always continuous, it's always smooth, it has no corners or cusps, which would be like sharp turns in your graph. Because it's a degree n, that means it has to have at most n x-intercepts. So it can't have more than n x-intercepts. The graph will also have the same tail behavior as the tail behavior of the dominating term. So when we get these really complicated polynomials, we're only going to need to look at that dominating term, that leading power, to determine what our tail behavior should be, because that's what's going to dominate the polynomial and therefore dominate the tail behavior as well. And then finally, if you have a degree n polynomial, then it will have at most n minus 1 relative extrema. What does that mean? It means that you're going to have at most n minus 1 maxes or mins, maximums or minimums. That's what the word extrema means, in between your n zeros that you have. So consider a real simple example here. Think about the graph of x squared. How many minimums or maximums does this graph have? It has one minimum, and this was a degree 2, so it has one less than the degree. If you think about a cubic, something like this is a degree 3 with, notice here, 3 zeros, at most 3 zeros. That was what statement number 2 up here said. And how many maxes or mins does it have? It has one max and one min, so a total of 2 extrema, which is one less than the power. And this one had one min, which was one less than the power. So that's what this statement number 4 means. You're going to have one less, at most, one less max, min, extremas total than what your degree was. So let's take a look at some more complicated examples. This first one is x minus 1 times x plus 3 times x. And the first thing that I would recommend that you look for are those x-intercepts. And this one is nice because it is already factored for us. So that means I can just look at it and see that this first factor is going to give me a solution or a root of x equals to 1. X plus 3 is going to have a solution of negative 3, and the factor x is just going to give me a solution of 0. So right away I know 3 dots on my graph. 1, negative 3, and 0. Then I like to look at the y-intercept as well, which is going to be when the x value is 0. So we're going to plug in 0 for this x, 0 for this x, and 0 for this last x. And it's that last x which is going to be the most important one, because it's going to take 0 times whatever these happen to be, so that means it's going to stay 0. So we have a y-intercept at 0, which we already knew as because we got that as an x-intercept as well. So the origin is both an x and a y-intercept. Then the last thing that you want to look at is that tail behavior, and this is going to be determined by the dominant term, and that's what this characteristic number 3 was talking about. No matter how crazy your polynomial gets, its tail behavior is always determined by that dominant term. Now, I'm not going to expect you to FOIL all this out, but in your head, imagine what would be the dominant term if you were to FOIL it out. Well, it would be this x times this x times this x. So the dominant term would be a positive x cubed. Since that's odd, with a positive coefficient, we know that its tail behavior has to be down on the left and up on the right. It has to rise up as we go left to right. So if I have only these 3 x-intercepts, and those are the only 3 I'm allowed to have because this is a degree 3 polynomial, then the one that's furthest on the left, I'm going to have to shoot down from there and stay going down, because I'm not allowed to turn back around and go back up, because that would give me another intercept. Likewise, on the right side, the rightmost intercept, this is the one where I'm going to have to shoot up from, and I can't come back down again because I'm not allowed to have any more intercepts. So there's where my tail behavior is coming from. And now all we need to do is sort of connect the dots. So remember that this is a cubic, so you should kind of have an idea of what a cubic graph looks like, and I sort of drew one over here as well. And you can just imagine that this is going to go up for a little ways, but then it's going to have to come back down again so that I hit this origin. And then this might go down for a little ways, but I'm going to have to turn back up again so that I hit my other x-intercept. So I have one max and one min, so that's two extrema for my cubic function. If you wanted to be more specific, you could always plot more points. You could try to locate the exact position of this max or this min, but really all I'm looking for is the basic sketch of the shape. You don't need to get too specific about plotting points. Alright, let's take a look at this next one. So we have x plus 2 quantity squared times x minus 1. So it's in a nicely factored form, which is going to make finding these x-intercepts fairly easy to do. This factor has as its solution -2. I'm going to make a note here. Notice that it has a power of 2 on it, so that means it has a multiplicity of 2. Okay? And then this factor would have a 0 at +1, and it was degree 1, so it's just going to have a multiplicity of 1. So that I know I've got an x-intercept at -2 and an x-intercept at +1. So let's plot those 2 points. Then let's find our y-intercept. So we're going to plug in 0 for this x, so it would be 0 plus 2 squared, and then 0 for this x, so 0 minus 1. 2 squared is 4, and 4 times -1 is -4. So this has to hit the y-axis at -4. And then let's look at our tail behavior. What's the dominant term if I were to FOIL this out? It would be this x, but notice, remember, it's being squared, times this x. So an x squared times an x would be an x cubed. And it's a positive x cubed, so that means we have to go down on the left and up on the right. So if I look at my 2 intercepts here, the one that's furthest on the left, this is the one that I have to shoot down from. And the one that's furthest on the right is the one that I have to shoot up from. If I were to imagine going up like this, then we would have to cross that x-axis at some point so that I could come back down and hit this y-intercept. And that would mean I'd have a third x-intercept, but we're only allowed to have 2. That's all we found. So it's not possible for me to go up from this x-intercept at -2 and go up from here and then come back down again. So what's the only way that I am going to be able to hit the x-axis at -2 and then come back down and hit this y-intercept? Well, the only way that can happen is if I shoot down on the left and then I just touch or bounce off that x-intercept and then immediately turn back around so that I can hit my y-intercept, and then I come back around and hit my second intercept. So notice that we had a bounce, what we're going to call a bounce, at -2, which is the factor that had a multiplicity of 2. And that's going to be important to notice when we do future problems here. Whenever the multiplicity is even, you will bounce off that intercept and you won't actually pass through the x-axis. You'll just touch it and then turn right back around again. And that always happens whenever you have an even multiplicity. If it's an odd multiplicity like our 1, which was multiplicity 1, then you will pass right through and go from negative to positive, or you could go from positive to negative. So we'll talk more about that as well, but you will see a lot of bouncing off your axis if the multiplicity is even. So these are the guidelines or the steps that you're going to want to take whenever you're trying to graph a polynomial function. First thing you're going to want to do is factor your polynomial completely to find all of your real zeros. These zeros are going to correspond to your x-intercepts on the graph. Now, based on what I just talked about, if that zero has an even multiplicity, then the graph will bounce off the x-axis. If the zero has odd multiplicity, then the graph will pass through the x-axis. Note that this means that the function changes sign when the multiplicity is odd and does not change sign when the multiplicity is even. Let me add one other comment here. The higher the multiplicity, so the higher that power is on that factor, and it doesn't matter whether it's even or odd, but the higher that power is, the flatter the graph will be at that intercept. So if you have a multiplicity of 6, for example, then that's going to bounce off your graph, but it's going to do it very flat like that, as opposed to if you had multiplicity of 2, then it might just turn around really quickly. Okay? So this might be degree 6 versus degree 2. Once you've factored and you've determined what your multiplicities are and you've determined what your x-intercepts are, you're also going to want to plot those x-intercepts and find your y-intercepts, noting the multiplicity. Then you're going to want to find your tail behavior, and then you're going to sketch a smooth curve that passes through the required points and has the appropriate end behavior. If you want to plot additional points, you certainly can. You could make a table of values, x's and y's, if you wanted a little bit more confidence about what your graph should look like, but it's not necessary. For this course, usually it's sufficient to just plot x-intercepts, y-intercepts, and use that tail behavior, and that's good enough. Alright, let's try some more. So this next one has x plus 2 quantity cubed times x minus 1 quantity squared. So the first thing we're going to do is find our x-intercepts. This first factor has as its solution -2, and note that it has a multiplicity of 3. Because that's odd, that means it's going to pass through. So it's either going to start negative and end positive, or maybe it'll start positive and end negative. We'll have to explore a little bit more to know which case it is. This factor over here has a solution of 1, and it has a multiplicity of 2. And because that's even, this is going to bounce off. Okay? Now one other comment. The multiplicity of 3, that's slightly large power, so it might want to show that it's a little bit flatter right around that x-intercept as we pass through, and I'll show you how we could show that in just a minute. Alright, we've got our x-intercepts. Let's go ahead and put dots on our graph for those, -2 and +1, and let's find our y-intercept next. So we're going to plug in 0 for these two x's. So if I plug in 0 for both of my x's, what's this going to reduce to? 2 cubed is 8, and -1 quantity squared becomes +1, so this is +8. So let's put a dot on the y-axis at 8. So way up here. Alright, now let's look at our tail behavior. First, we need to figure out what our leading term or our dominant term would be, and that's going to be this x quantity cubed times this x quantity squared, and an x to the third times an x to the second. Remember, you add powers when you're multiplying the bases, so this would be an x to the fifth. Since it's an odd power with a positive coefficient, it's going to start low and end high. So since I only have these two intercepts, the one on the left I'm going to have to shoot down, going down, and the one on the right is where I'm going to have to shoot up from, like that. And now we need to connect through our intercepts. So remember, at -2, this was a odd multiplicity, so we're supposed to pass through it. We're not going to bounce off here. We're going to go ahead and pass through so we can carry on and go ahead and hit that y-intercept. But because it was slightly higher in power, it was a multiplicity of 3, you might want to sort of exaggerate that flatness just a little bit. So maybe I'll revise how I've drawn this and do something like this. I'll kind of flatten it out a little bit, and I'll come up like this, and I'll come down like this. So there's my little flat part. And then remember, at +1, this was an even multiplicity, so we do want to bounce off here. So this is going to just bounce off like that. So this graph would have to come down, hit at 1, and then immediately bounce back up and shoot up from there. So there's my graph. Okay, let's try another one. These take a little bit of practice. So on this next example, again, starting with your x-intercepts, this first factor has as its solution -2/3, and it has a multiplicity of 2, and because that's even, we want to bounce off right at that point. And then this factor right here has as its solution +1, and it's a multiplicity of 1, which is odd, so here we're going to pass through. So let me put my dots on. I'm going to have a -2/3, just estimate where that would be, and +1. Let's find our y-intercept. So I'm going to plug in 0 for this x, so this whole 3x term becomes a 0, but I have that +2 and a quantity squared, and then this would become 1 minus 0. So 2 squared is 4, and 4 times 1 is going to stay 4. And then we need our tail behavior. So in this first factor, we do have a coefficient in front of that x. So it's going to be this 3x quantity squared times this, which also has a coefficient because it has an implied negative in front of it, times another -x. So 3 squared would be 9, but it gets multiplied by that -1. So this becomes a -9, and then we have an x squared times an x, which is an x cubed. So make sure you take those coefficients along with you, because in this case it's important to note that this coefficient is negative. So since it's odd, we want to go either up, down, or down, up, and because it's negative, we want to start up and then end down. So that's what our tail behavior should look like. On the leftmost x-intercept, this is the one where we're going to be shooting up from, and the rightmost one is the one where we're shooting down from. We had a bounce at this -2/3. Whoa, sorry about that. Crazy pen. And so if I bounce off here, I'm just going to touch at -2/3 and immediately turn around, hit that y-intercept, then I have to come back down again to hit that other x-intercept, and I just pass right through. So there's my graph. Alright, let's try one more example like this, and this one has a lot. So we've got all these different factors. Let's go ahead and start with our x-intercept first. So this factor, even though it doesn't have anything added or subtracted from it, it's just an x, it will contribute a 0. This factor has as its solution 1, and it has a multiplicity of 2. So that is going to cause us to bounce off at +1. What's the solution to 4 minus 3x? Well, if I were to set it to 0, I'd have to add the 3x over, divide by 3. So this has as a solution 4/3, and it's to the first power, so just a normal factor. And then the last factor has as its solution -4, but it has a multiplicity of 3, which is odd, so it's going to pass through. But because it's 3, which is a slightly bigger number, it's probably going to be a tiny bit flatter right at -4 on that x-axis. So let's put in our intercepts. We have 0, we have 1, we have 4/3, which is just a little bit bigger than 1, 1 1/3, and then we have -4. Okay, let's find our y-intercept. That one should be fairly simple because if I'm plugging in 0 right away, if I put a 0 right here, this 0 is going to multiply all of these guys times 0. So 0 times anything is going to stay 0. And so I have that y-intercept right at the origin, which we already knew about from that x-intercept. And then finally the tail behavior. So we need to look at all of our dominant terms from each of our factors. So we're going to get an x from this one. We're going to get an x squared from this one. Take the coefficient here as well. We're going to get a negative 3x from the third factor. And here we're going to get an x cubed on the end. So we get a coefficient of a negative 3, and we get an x squared, an x, and an x cubed. If I add all those powers, I get 1 plus 2 is 3, 4 and 3 is 7. So I get a negative 3x to the 7. So it's odd, but it's negative odd. So I want to start high, and I want to end low. So my leftmost intercept is going to start going up and to the left, and my rightmost x-intercept is going to be shooting down. So now we want to connect our dots here, starting at the negative 4, and that was the one that had a multiplicity of 3. So we were supposed to pass through, but it was supposed to be a little bit flatter. So again, let me erase this for a moment and let me exaggerate that flatness just a little bit. So I just like to put a little sort of flat line segment there, and then this is going to shoot up and to the left, but we are supposed to pass through, so it's going to come down again. But my next intercept is right at 0. Am I supposed to bounce or am I supposed to pass through at 0? Well, it was x to the first, so I am supposed to pass through on this one. So I am going to have to turn back around to go through and continue going up and pass through. Then I would hit 1, which is where I'm supposed to bounce off. So if I come back down to hit that 1, I have to immediately turn around and bounce back up again. But then I have to turn back around and come back down through 4/3, and that was one that we were supposed to pass through. So just to kind of recap, we came through here at negative 4 a little bit flat, but I continued passing through, hit 0, continued passing through, went up a little ways, but had to turn back around so I could bounce off at 1, and then turned around again really quickly so that I could pass through 4/3 and continue going down from there. So there's my graph. Lots of twists and turns because of all these different factors. Okay, a couple of last questions here, just to kind of pull together everything that we've talked about. Here's the graph of a polynomial. Could this be the graph of a degree 3 polynomial? And if so, how do you know? If not, how do you know? So what are some of the things that you could think about? There's a couple ways to answer this question. One of the things that I immediately see when I look at this graph are some intercepts. I see one right about here, one here, and one here. So let's kind of estimate where those are. I'm going to say that this one on the left is at negative 3, and then I've got one here at 2, and then I've got one here at 6. Now, based on how the graph is reacting at that intercept, what kind of multiplicities would these have to have? At negative 3, the graph bounced off. So this has to have even multiplicity. At 2, the same thing. It bounced off right there. So it would also have to have even multiplicity. And then at 6, it does pass through, so this would be odd multiplicity. Now we don't know exactly what the equation of this polynomial is, but one guess might be what kind of factors. So let's say that this polynomial has what factors? Well, if I know that it's supposed to have -3 as a 0 or an x-intercept, then that means it has to have x plus 3 as a factor, but we said it had to have even multiplicity. So at a bare minimum, this would have to have at least a square on it. Maybe higher even if we had something fairly flat. It could be higher. It could be to the 4th or to the 6th. What would the factor have to be if I have an x-intercept at 2? Well, if I want a solution of positive 2, then I need to have a factor of x minus 2. And again, that has to have an even multiplicity because there was a bounce. So at the very minimum, it would have to be at least a square. And then finally, at the x-intercept of 6, I would have to have a factor of x minus 6, and this was an odd multiplicity, so this could be just to the 1st power. So at the very minimum, this would be at least what my function would have to have involved in it. So what would be the leading degree here? What would be the dominant term if I were to FOIL this out? This would have degree x squared times another x squared times an x to the 1st, which would make this at least a degree 5. So this graph is at least a degree 5 polynomial. So the answer to this question of whether this is a degree 3 polynomial, it has to be no. Now, one other consideration that you could think about to answer this question in a slightly different way would be to look at the maxes and the mins. So if we count how many maxes and mins we have a min right here, and a max right here, a min right here, a max right here, and a min right here, and I don't have any more maxes or mins on the side. So how many total extrema, which means all the maxes and the mins together, how many total do I have? I have 4. And remember from earlier on, let me see if I can find it back in our notes. Up here, we said in option number 4 here that a graph will have at most n minus 1 relative extrema if it's a degree n polynomial. So if a graph has 4 relative extrema, then it would have to have at least a degree 5, which is what we came up with our other conclusion, with our other argument. So if we have 4 extrema, then that implies that this has to be at least a degree 5 polynomial. Okay? So that would be another correct argument as well. So you can either look at intercepts and count up their multiplicities to figure out what your degree would need to be, or you could count up your extrema and add 1 to that, and that would have to be the bare minimum of what your degree of your polynomial is as well. So you could do this argument either way. Okay, last example. Here again is the graph of a polynomial, and what we want to do is come up with a formula for what this could possibly be. And there's more than one solution here because we don't even have a y-axis going on, so we don't know the actual scale here, but we're going to just come up with one possibility for what the equation would be for this graph. So here's my equation, and I'm going to put a 0 in here so it's a little more obvious. There's x equals 0, and then I'm going to the right and to the left. So what are some of the things that we would want to consider? Well, if we want to know a formula for a polynomial, it's a nice way to write a formula for a polynomial is to write it in its factored form, which means we would need to know where the zeros are. So let's find the zeros of this graph. We know that we have a 0 here at -4, and because it bounces off at -4, we're going to have an even multiplicity. Then the graph goes down for a little ways, and then it hits 0. So we've got an intercept at 0, and this one passed through from negative to positive. So this has to be an odd multiplicity. Then we continue along, and we bounce off right at 3. So since it's a bounce, we would have to have even multiplicity. And then I go up, and I come back down and I hit at 7, and I pass through at 7, so this is going to have odd multiplicity. So very similar to what we did in the last example, let's make a guess for at least one possibility for what this function would have to have as its equation. If I want to have a solution or a 0 at -4, then I would have to have a factor of x plus 4, and it needs even multiplicity, so I would have to have at least a square on there. Then I want a 0 at 0, so my factor would just have to be x. And that's an odd multiplicity, so I'll just leave it as x to the first. Then I need a 0 at 3, so I would have to have a factor of x minus 3, and that's an even multiplicity, so let's make it have a power of 2. And then 7 has to have a factor of x minus 7, and that was an odd multiplicity. Again, this is just one possibility. You could change these powers to other even powers or other odd powers, and it would still have this possibly as its graph. So here's our answer, but there's one last thing that you want to double check before you put a box around your solution, and that's the tail behavior. Look at the tail behavior of our graph. It goes down on the left and it goes down on the right. So we want our tail behavior to be down, down. What kind of polynomials have tail behaviors that go down, down? They are tail behaviors of even powered, something even, but negative leading coefficient. If it was positive, then it would have been up, up. So what we want to make sure of is that we are generating the correct tail behavior with our guess right here. So let's look at what our power would be. We've got an x squared from this factor. We have an x, we have an x squared, and we have an x. So square 2, 3, 4, 5, 6, this would be an x to the 6th. So it is even. That's good news. However, if I leave it like this, this would be a positive x to the 6th, and that would mean we were supposed to have tail behavior of up, up, and we want it to be down, down. So how can we fix this? How can we make it so that we aren't changing any of the zeros, we're not losing any of the zeros or losing any of their multiplicities, but we're just making sure that we have this same graph but flipped over so that we have a tail behavior that goes down, down. Easy way to fix it? Multiply by a negative. So if I put a minus in front like that, then that's going to carry down to my negative x to the 6th, and now my tail behavior will be going the right way. It'll be going down, down like I want it to. Okay? So by just throwing in that minus sign, we fixed it so that we're maintaining the right tail behavior, we're maintaining the right zeros, and we're maintaining the right multiplicities. So that's one possible solution for what the equation would be for this polynomial. All right, good job. We've finished up our video lecture on polynomials. Good luck.